Lecture 4.1, Extreme Values of Functions. This is the Rio Tinto boron mine, formerly the U.S. borax boron mine, located near Boron, California. It is the largest open pit mine in California and the largest boron mine in the world. This mine is located at the western edge of the Mojave Desert. To get here, you drive a long ways on a freeway with very little traffic, and people tend to speed. In order to get drivers to slow down as they come into the parking lot, they have a series of gradually decreasing speed limit signs, and they used unusual values to get drivers' attention. The textbook gives the following example at the start of Chapter 4. The mileage of a certain car can be approximated by m of v equals 0.00015 v cubed minus 0.032 v squared plus 1.8 v plus 1.7. At what speed should you drive the car to obtain the best gas mileage? Of course, this problem isn't entirely realistic, since it is unlikely that you would have an equation like this for your car. We could solve the problem graphically. If we choose our window settings, so x goes from 0 to 100, representing 100 miles per hour, and y goes from 0 to 50, representing miles per gallon, we get this curve. On the TI-nspire, we use menu 6 analyze graph 3 maximum. We choose lower and upper bounds, and the calculator finds our answer. So there we see the car will get approximately 32 miles per gallon when driven at 38.6 miles per hour. Notice that at the top of the curve, the horizontal tangent has a slope of 0. Traditionally, this fact has been used both as an aid to graphing by hand and as a method to find maximum and minimum values of functions. Even though the graphing calculator and the computer have eliminated the need to routinely use calculus to graph by hand and define maximum and minimum values of functions, we still study the methods to increase our understanding of functions and the mathematics involved. Absolute extreme values are either maximum or minimum points on a curve. They are sometimes called global extremes. They are also sometimes called absolute extrema. Extrema is the plural of the Latin extremum. Extreme values can be in the interior or the endpoints of a function. In this example, y equals x squared, where the domain goes from negative infinity to positive infinity. We have an absolute minimum at 0, 0, but no absolute maximum. The function just keeps increasing. If we change the domain to go from 0 to 2 in a closed interval, we see that we have an absolute minimum value of 0 and an absolute maximum value of 4. In this case, the global minimums and maximums are at the endpoints. Now changing the domain so that the interval is open at the left-hand side, we see the graph has an open circle at the left end. So there is no minimum. It approaches 0, but there is no actual minimum value. There is still an absolute maximum, however, at y equals 4. Now, when we use an open interval at both ends, we have open circles at both ends. At the left end and the right end. So, there's no minimum and no maximum. That is, no specific value we can state as the minimum or the maximum. The extreme value theorem says that if f is continuous over a closed interval, then f has a maximum and minimum value over that interval. It is important to note that the function must be continuous and the interval must be closed. If either of those requirements are not met, then the extreme value theorem does not apply. Looking at some examples, and in all three of these examples, I didn't draw in the solid dots at the end, but we will assume that they're closed intervals. In this first example, the maximum occurs at an interior point, and the minimum occurs at an interior point. In this next example, both the maximum and minimum occur at endpoints. And in our third example, the maximum occurs at an interior point and the minimum at an endpoint. So we have the maximum here at an interior point and the minimum at the endpoint. Local extreme values. A local maximum is the maximum value within some open interval. A local minimum is the minimum value within some open interval. An example from real life might be the pitcher's mound in a baseball field. Even though it might not be the highest point in town, it is the highest point within the baseball field. So in this example, we have an absolute minimum, which is also a local minimum, a local maximum, a local minimum, an absolute maximum, which is also a local maximum, and a local minimum. And once again, we're assuming closed interval. Local extremes are also called relative extremes. Notice that local extremes in the interior of the function occur where f prime is 0, for example, here, or here, or where f prime is undefined, like this one. So we see there f prime is 0, and the slope is 0. Local extreme values. If a function f has a local maximum value or a local minimum value at an interior point C of its domain, and if f prime exists at C, then f prime c equals 0. That is, the slope is 0. Critical point. A point in the domain of a function f at which f prime equals 0 or f prime does not exist is a critical point of f. Note, maximum and minimum points in the interior of a function always occur at critical points, but critical points are not always maximum or minimum values. Example 3, finding absolute extrema. Find the absolute maximum and minimum values of f of x equals x to the 2/3 on the closed interval -2 to 3. We start with f of x equals x to the 2/3. Use the power rule to get f prime x equals 2/3 x to the -1/3. Which we could rewrite f prime x equals 2 over 3 cube root x. There are no values of x that will make the first derivative equal to 0. However, the first derivative is undefined at x equals 0, so 0, 0 is a critical point. Because the function is defined over a closed interval, we must also check the endpoints. At x equals 0, f of 0 equals 0. To determine if this critical point is actually a maximum or minimum, we try points on either side without passing other critical points. f -1 equals 1, f1 equals 1. Since 0 is less than 1, this must be at least a local minimum and possibly a global minimum. At x equals -2, f of -2 equals -2 to the 2/3, which is approximately 1.5874. At x equals 3, f of 3 equals 3 to the 2/3, which is approximately 2.08008. So we see that of the three choices, which are 0, 1.5874, and 2.08008, the smallest one is 0, so we have an absolute minimum at 0, 0. The absolute maximum is the largest of these three values, so we have an absolute maximum at 3, 2.08. And this is the graph of that function. We see that we have an absolute minimum at 0, 0, and an absolute maximum at 3, 2.08. Finding maximums and minimums analytically. Step 1. Find the derivative of the function and determine where the derivative is 0 or undefined. These are the critical points. Step 2. Find the value of the function at each critical point. Step 3. Find values or slopes for points between the critical points to determine if the critical points are maximums or minimums. And step 4, for closed intervals, check the endpoints as well. Critical points are not always extremes. In this function, y equals x cubed, we see a critical point at 0, 0, because the slope is 0. However, it is not an extreme. However, for y equals x to the 1/3, at the point 0, 0, f prime is undefined. It's also not an extreme.